Electronegativity decreases as you go down a group on the periodic table. But why? Let's start by going over the definition of electronegativity. Electronegativity is the ability of an atom to attract shared electrons to itself. In other words, it's the effective nuclear charge on bonded electrons. Every atom is assigned a numerical value for its electronegativity. Those values do not have a unit. Also, remember that because noble gases do not bond, they are not electronegative. Here we have the Pauling scale, which assigns a numerical value for each element. As you can see, atoms have more electrons and shells as you go down a family on the periodic table. The more shells present, the further the valence shell is from the nucleus, and the valence shell is where the electrons that bond come from. So the best way to illustrate the fact that the number of shells and the distance between the valence electrons and the nucleus increases as you go down is by using the shell model. However, it is important to remember that according to the quantum mechanical model, electrons are not actually in the formation depicted by the shell model. So as you have seen, as you go down the periodic table, the main observable difference is that there are more shells added. Therefore, the main reason why going down a column on the periodic table decreases the electronegativity is because there is an increase in the number of shells. But how can we provide evidence that that is true? By using Coulomb's law, of course. Coulomb's law states that the magnitude of the force of attraction is inversely proportional to the square of the distance between them as shown by the equation, where F is force, K is a constant, Q1 is a charge, in this case the charge of the nucleus, and Q2 is another charge, in this case the charge of the bonded electron. The resulting force is a negative value which denotes attraction because electrons are negatively charged and protons are positively charged. Coulomb's law allows a person to see that the larger the distance between the bonded valence electron and the nucleus, the smaller the force. For example, if the radius of an atom was 2 versus if the radius of a different atom was 4, the force would be greater on the atom with a radius of 2 as per the math shown. However, as the number of shells increase, not only does the distance between the nucleus and valence bonded electrons increase, but so does the number of electrons between the nucleus and the bonded electrons. Because electrons have the same charge, they repel each other and further increase the distance between the bonded electrons and the nucleus. That phenomenon is called electron shielding. Electron shielding contributes to the decrease in attraction in atoms lower on the periodic table. But the number of electrons participating in electron shielding is not simply equivalent to the number of shells there are between the valence electrons and the nucleus, as you can imagine if you visualize the Bohr model, because shells are not actually as the shell model depicts them. The quantum mechanical model is a better depiction of the location of electrons in an atom. The presence of subshells, as described by this model, means that there will be a significant amount of electron shielding happening. As you can see in this diagram of magnesium per the quantum mechanical model, a valence electron will be separated from the nucleus for what is likely more than 3 electrons. So to recap, electronegativity decreases as you go down a group in the periodic table. Why is that the case? Because the distance between the bonded electron and the nucleus is increased. It is increased due to an increase in shells and electron shielding, and the reason why that greater distance decreases the electronegativity is because Coulomb's law states that the force, which in this case is electronegativity, is inversely proportional to the distance.